But as you can see above, the schedule has changed. So now I'll be lecturing instead of Pierre Charolois on Fermat's last theorem, sort of to lay some of the groundwork for his lecture, which has now been pushed to the 5:30 to 6:30 slot. And then after that, there will be this barbecue. Okay, so the topic now I want to discuss in this last lecture of this week is Fermat's last theorem. So we want to consider the family of curves, where a very well-known classically family of curves, the so-called Fermat curve, x to the p plus y to the p equals z to the p, where p, for the purposes of the lecture, is going to be a prime greater or equal to 3, I guess. So this collection of curves is a bit sort of analogous to the family of curves y1 of p, which we studied yesterday and today in my lectures and the lectures of Marussia Reboledo. And so for this, so it's also indexed by a prime p. And we want to prove a theorem of a similar flavor, namely that if p is large enough, there are no rational points on this curve. So that's Fermat's last theorem. That's going to be the topic of today's lecture. So this is the celebrated Theorem of Wiles, that this equation has no rational solutions, non-trivial. So xp plus yp equals zp has no non-trivial rational solution for p greater or equal to 3. So by non-trivial, I mean that the product xyz should be non-zero. So I don't want zero coordinates. Okay, so to motivate the approach, sort of the general strategy which is used to prove this theorem, which if you see it for the first time, well, it might seem a bit surprising or at least serendipitous, I want to recall some of the ideas that were introduced in Hugo Chapdelain's lecture on Monday. Okay, so remember, so this is a sort of a bit of motivation for what I'm going to say shortly. So motivation for the approach that I'm going to describe. So in Chapdelain's lecture, we learned that there's a kind of bijection, or there is a correspondence. I mean, correspondence in the non-mathematical sense of the word. I mean, so there is a correspondence between two things. Between on the one hand, strategies for studying the primitive solutions to the equation xp plus y to the q equals z to the r. So the setting of Chapdelain's lecture was a little bit more general than the classical Fermat equation, in the sense that we were allowing the exponents to be different, but we were insisting on solutions being primitive, which meant that they had no prime divisor in common. GCD xyz equals 1. And so what Hugo explained in his lecture is that basically you have a collection of strategies for tackling this equation, one for each unramified covering of p1 minus 3 points, p1 minus 0, 1, infinity, of signature PQR. And to remind you briefly of what Hugo explained on Monday, so the idea was that you would associate to the collection of all solutions of this equation a certain subset, which Hugo called sigma PQR. That was just a set of all rational numbers of the form a to the p over c to the r as ABC ranges over the primitive solutions to the generalized Fermat equation. And we viewed that set as a subset of the projective line over q, minus 3 points if you want. And then what Hugo showed is that if we gave ourselves a covering pi from x to p1, which was of signature PQR, then pi inverse of this set, sigma PQR, was contained in X of L, where L was a number field whose ramification and degree, of course, could be bounded a priori. Okay, so L has ramification bounded independently of the solution. So a priori, there might have been infinitely many solutions, but the ramification in the set was bounded independently of the solutions. And therefore, by Minkowski, or by Hermite, it was a finite extension. And from that, of course, we could conclude that the finiteness of the rational solutions to this equation from Falting's theorem that this set is finite. Okay? So that was what Hugo explained in his lecture. So armed with this insight, we could sort of, and now we want to study the classical Fermat equation, so we could ask, what are the various unramified coverings of P1 minus 3 points of signature PPP? So what are some coverings of P1 minus 0, 1, infinity of signature PPP? So with ramification indices of order P above the 3 deleted points. Well, the first example of such a covering is to take for x the Fermat curve itself, xp plus yp equals z to the p. And for pi, take the projection which to a point x, y, z associates the ratio x to the p over z to the p. Okay, so it's an exercise to check that pi has signature PPP. Pi is of signature PPP. And sure enough, if you take a point now in sigma PPP, corresponding to a solution to the Fermat equation, then indeed its inverse image, it lifts to a number field of bounded ramification. In fact, it lifts to a rational point, right? It lifts to Q. And so this kind of gives rise to the tautological, if you want, approach to Fermat's last theorem, where you try to study solutions to the Fermat equation by studying rational points on the Fermat curve. Just a geometric reformulation, right? But the whole, I mean, what turned out to be the key to the solution of Fermat's, to the proof of Fermat's last theorem eventually, is that this is not the only covering of signature PPP. There are infinitely many different ones. And there's a particularly nice one which can be described in terms of modular curves. So the second example, which turned out to be the key to Fermat's last theorem, is to use modular curves to consider the covering x of 2p over x of 2. So x of 2p here is the moduli space of elliptic, well, let me just say what x of n is in general for any integer n. It's the moduli space consisting of triples given by an elliptic curve together with a basis p1, p2 of points of order n. So of classifying these triples where p1, p2 is a basis, a z mod n basis of the set of n torsion points on E. Well, this is actually, you can show that this moduli problem is representable, and the representing functor is this modular curve, x of n. Now, the x of 2 has a very explicit description, or at least over the base z of a half. So over z of a half, I can write x of 2 as the spec of z of a half adjoining the lambda, where I've removed 1 over lambda and 1 over lambda minus 1. In other words, it really is p1 minus, this is y of 2. So if I look at the open modular curve where I omit the cusps corresponding to curves with degenerate reduction, y of 2 is the spec of this ring, And the universal elliptic curve over this is the so-called Legendre curve with equation given by, so the universal curve, or maybe, let me put uni in quotes. It's a kind of, it's not quite a moduli space. So the universal curve is y squared equals x minus 1, x minus lambda, lambda being this parameter. So if you compute the discriminant of this curve, you'll see that it's some power of lambda times some power of lambda minus 1. This curve has a good reduction outside. So over this ring, it has good reduction. It's really an elliptic curve over spec, over y of 2. Okay? So, okay. So let's see. So now let T be a typical element, which I'm going to write as a to the p over c to the p in sigma p, p, p. So here a to the p plus b to the p is c to the p. So this is a solution to the Fermat equation. Here a, b, c are integers, and the GCD, well, I've chosen them so that the GCD is equal to 1. So, so if I take, maybe I should call this lambda rather than t. So if I take the point on x of 2 corresponding to this value of lambda, and I ask for the field of definition of, the sort of the fiber for this pi above this lambda, what I get is basically the field which is cut out by the p division points. So pi inverse of t, pi inverse of lambda, is defined, or any lift is defined over the field of p division points of the curve, of the elliptic curve y squared equals x minus 1, x minus this lambda, which is a to the p over c to the p. Okay? So we're led rather naturally to consider this p division field associated to this particular elliptic curve. Now, for technical reasons, it's going to be better to work with a curve which is actually isomorphic to this one over q bar, but not necessarily over q. So I'm going to take a twist of this curve. So it is better. So what we're going to try to do, you see, we're trying to choose the curve in such a way that the mods, that the p division field is as little ramified as possible, has as little ramification. So for that, it is better to work with the curve given by the equation y squared equals x minus a to the p, x minus c to the p, where a and c have been chosen. So A has been chosen so that it's, I think this is 0 mod 4, and C is minus 1 mod 4. So you can always take your solution to Fermat's equation, permute around the ABC, and adjust the signs if necessary so that these congruents as mod 4 are satisfied. And so you write this particular equation down. Okay? So maybe as a, so I'm going to call this curve EABC. This is what's called the Frye curve associated to the solution ABC to Fermat's equation. So, it's an easy exercise. The fact that these two curves are isomorphic over the field which you obtain by adjoining the square root of ABC or something. Okay? So these are isomorphic over q bar, but not over q, and we're going to work with this one, which is somehow a bit nicer. Okay, and also that's one thing. And another point is that rather than considering p division fields, it's a sort of a well-accepted principle in arithmetic now that it's much better to talk about representations of the Galois group. We already saw that when I explained Falting's theorem on the third day of the lecture series, where I introduced the notion of an analytic representation associated to an abelian variety. So here too, instead of talking about the p division field, we're going to, instead of talking about this fiber, so to speak, we're going to talk about the mod p representation. So we will consider the representation of the Galois group, which I'll call rho ABC, which maps the absolute Galois group of Q, the Galois group of Q bar over Q, to the automorphisms, the FP linear automorphisms of the group of p division points of this elliptic curve of EABC. And this is identified, since this is naturally a two-dimensional FP vector space, and the Galois action preserves that. This is identified, the image is identified with GL2 of the finite field with p elements. Okay? And so the idea which I wanted to convey in this kind of motivational part was that this representation should have very little ramification, at least if you believe in the principle that was explained in Hugo Chapdelain's lecture on Monday. Okay, so now we're going to make that precise in this particular case because we have so much control over these modular curves and we understand a lot about the arithmetic of elliptic curves, we can actually make that very precise. So what do we know about this representation, rho ABC? So the first result, which I call a theorem, I mean, it's really not, I don't know, maybe I should call it a proposition or something. The key point about this theorem was realizing that its interest, its relevance to the problem of studying Fermat's last theorem. I mean, in itself, it's not hard to prove, as we'll see. So this was maybe first noticed, I guess, by Frye. I'm not completely sure of the history of the ideas around this result. So this is sort of an analysis of the local properties of rho ABC. So what we sort of have from Hugo's lecture of Monday is that we know that there's going to be some finite set of places of Q, some finite set of primes, such that all these rho ABCs are going to be unramified outside that finite set S, and that set S is not going to depend on the solution ABC. At least if you believe the statement I made about the geometry of this covering, that it's indeed a signature PPP. Okay? Now we're going to prove that actually independently of knowing that. Okay? We're going to sort of give you a direct proof of that. And in fact, we're going to say something more precise. We're going to say that we're going to show this representation is unramified outside only two primes, 2 and p. So the bad set consists of only 2 and p. The second point is that, okay, well, now there are these two bad primes to consider. So I'm going to show that rho ABC restricted to a decomposition group at 2, so the Galois group of Q2 bar over Q2. So here, by D2, I mean the Galois group of Q bar over Q2, which I think of as a subgroup of the Galois group of Q by fixing an embedding of Q into Q2 bar, of Q bar into Q2 bar. Okay? So this is just a restriction. This inclusion is just a restriction of automorphisms. So rho ABC restricted to D2 is isomorphic to the following sort of reducible upper triangular representation. So I'll explain what these symbols mean shortly. So I have something like this, some stuff up here, and a 0 there. Okay, so what I mean by that is that if I evaluate this on an element sigma, I get this kind of matrix, where chi cyclotomic is the character on the Galois group of Q2 bar over Q2 to the automorphism group of mu p. So describing the action of this Galois group on the p roots of unity. So that's what's commonly called the cyclotomic character, the mod p cyclotomic character. And psi is just an unramified character. So it factors through the quotient by the inertia group. So it's sort of nothing much. And star is just some function, on the Galois group, which might be ramified. So actually, you'll know that on both these entries, both these characters of the Galois group are unramified. The cyclotomic character is unramified at 2, okay, because p is not equal to 2. But you might have ramification coming from here. Okay, so there's a certain amount of ramification going on at 2. So one often says in the sort of this is technical terminology that rho ABC is ordinary at 2. So that's just a word that means that exactly this, that it has this upper triangular appearance when you restrict to the decomposition group at 2. And then finally, the third thing is that rho is either ordinary at P. So now I want to describe the behavior at P. So the restriction of rho to the decomposition group at P is either ordinary or what's called finite. And here, finite means that it comes from the Galois action on the points of a finite flat group scheme over ZP. Okay, so, I mean, those who don't know about finite flat group schemes, don't worry about this condition. But what it sort of means basically is it looks like the kind of representation you would get if you took the points of order P on an elliptic curve having good reduction at P. So if you take a curve with good reduction at P and you look at its P division points, you can't expect that representation to be unramified. For example, the mod P cyclotomic character is going to appear as a determinant of this representation, and that's a ramified at P. But there's a condition which one can describe precisely on the restriction of the decomposition group at P, which sort of characterizes those representations that are coming from varieties with good reduction. Okay, and that's in this context, that's how you can state it. Okay, so I'm going to actually now prove this result, sort of show to you that, so what I said before about this thing having bounded ramification is kind of independent of the proof I'm going to give, which is going to be based on the theory of elliptic curves. Are there any questions? Yeah. A finite flat group scheme over ZP, over the base ZP. So, so this two-dimensional vectors. So if E is an elliptic curve with good reduction, the point is that this P torsion is a group scheme, okay? And the Galois representation is coming by looking at the action of the Galois group on the generic fiber of this. But this group scheme extends to a finite flat group scheme over ZP. It sort of has good reduction at P. That's what, because the elliptic curve has good reduction at P. So there's a way of this, of kind of describing in a fairly concrete way what that means in terms of the theory of finite flat group schemes. So ordinary means exactly that it looks like this. Okay? Same thing for P. Ordinary at P means that you're going to have the same appearance. You have a cyclotomic character here, some unramified characters here, and it's upper triangular. Yes, so it's the kind of thing that you would get by looking at the Galois representation on a semi-stable elliptic curve. And I'll explain that now in the proof. Okay. Okay. Okay, so let me now give you a proof of that. If L does not divide 2ABC, okay, I should say when one has to make a calculation. Okay, so this Frye curve, this curve EABC, which I wrote down here, you can compute the various invariants associated to it, namely its discriminant and its conductor. And the discriminant of EABC turns out to be 2 to the power 8 times ABC to the 2p. So you just write down the discriminant, you'll see you get that. And the conductor, when you analyze the conductor, It's the radical of ABC, meaning the product over all primes L dividing ABC of L. So you pick up every prime L with multiplicity 1. Okay, note that 2 appears here because ABC is even. Okay, so those are the sort of basic invariants associated with the elliptic curve. So, in particular, if L does not divide 2ABC, then E, ABC, has good reduction, which implies, at L, which implies that the representation rho ABC is unramified. That's a general property of the Galois representation associated to the torsion of an elliptic curve, is unramified at L. So the interesting case occurs sort of when we consider primes L that divide ABC, and let me assume here that L is not equal to 2 or P, okay? Then, so these are primes where the elliptic curve, EABC, has bad reduction. So you'd be sort of entitled to expect that the mod P representation also has some ramification. But in fact, it doesn't. So those primes drop out of the ramification set of the associated P division points, and that's really what makes the thing work. So, so why is that? Well, then we can, so if L divides ABC, that implies that the elliptic curve EABC has multiplicative reduction at this prime, which I'm calling L. It has multiplicative reduction at L, sort of, the prime L divides the conductor with multiplicity 1, so there's an algorithm of Tate for analyzing the singular fibers of an elliptic curve, and in this case, it implies that the curve has this kind of multiplicative reduction. And then we have an explicit description of the set, say, of points of the elliptic curve over, say, the maximal and ramified extension of QL. So if I look at E of QL and ramified, this is isomorphic to the multiplicative group, QL and ramified star, modulo a discrete subgroup generated by the powers of a certain element, Q, where Q is a so-called Tate parameter. And, so it's the Q which corresponds to this point, right, in the moduli space of elliptic curves. It's the same local parameter that occurred in my talks yesterday and in Marussia Reboledo's lecture today. So the relation between Q, so this Q belongs to L ZL. So it's an element which is in ZL but divisible by L. And there's a relation between Q and delta. Namely, delta is Q times the product of 1 minus Q to the n to the power 24. Okay, that's something that we saw before. So this is just the discriminant of the Tate curve. And in particular, from this, and this makes sense in LZL because this is a unit and this converges in QL. And what you see from this is that the ORD L, the multiplicity with which L divides Q, is the same as the multiplicity with which L divides delta, and delta is a Pth power. That's crucial, right? So delta is essentially a Pth power. Certainly, the number of times L divides delta is divisible by P. So this ORD L of Q is congruent to 0 modulo P. So, so here we've used, this is the so-called Tate model. For the elliptic curve, E over QL. So we're exploiting here the fact that E has multiplicative reduction so that in the fiber above L of the modular curve, it meets the section infinity for or one of it meets a cusp over the fiber at L. Okay, but now from this description, you can easily analyze the module of P division points. Okay, so E of QL bar P is defined. So the individual points, the physical points on this module, so the points in this are defined over the extension that I get by adjoining to QL, or maybe to QL unramified, because this description is over QL unramified. What? I have to adjoin all the elements whose pth power is going to give me Q. For that, the p division points are all the things of the form zeta to the A times Q to the B over P, where A and B run between 0 and P minus 1, if you want. Okay? And zeta is just a primitive pth root of unity. Zeta P equals 1. Well, so I didn't even have to adjoin it here because the pth root of unity is unramified over QL, so it already belongs to QL unramified. The main point for this extension is just QL unramified, to which I've adjoined the pth root of Q. But Q is of the form, L to some power times a unit at L, a unit in ZL. And the power that occurs is P times something, P times T. So if I take the pth root of this Q, I don't acquire ramification at L, which I would only do if I had some other power of L, not divisible by P in the exponents. So you just see that this extension is unramified at L. It's unramified at L. Well, so this is equal, in fact, to QL unramified, okay? So all the p torsion points are already defined over QL unramified. That's what you see by looking at this analytic description over QL of this elliptic curve. So that's the proof for part 2, which is really the main. Which ones? These? Yeah, well, because here I'm just taking a pth root of unity. Now, it's known that L is unramified in the field of pth roots of unity. So the pth roots are, and then this Q, it's of the form L to some power times a unit at L. If I take the pth root of a unit, I get something unramified.
No, sorry. Why are those points defined
over this? Because this EL, this elliptic curve is this thing, right? Analytically over QL. So now I look at, what's the p torsion in this group? It's all the elements of this form. Okay.
All right.
And yeah. This isomorphism is defined over QL on RAM. It's even defined over a smaller extension. Okay. So, then I'll just quickly gloss over the last 2 points, which are comparatively less important. The case where L equals 2 and P. So 3, if we consider the case where L equals 2, well, again, 2 always divides the conductor. So the elliptic curve has multiplicative reduction at 2, and so you can also use the Tate model to derive this description. So use the Tate model, and this I leave to you as an exercise. So you have to find a good basis which is stable under the action of gal Q2 bar over Q2. In this sense, right? You have to find a vector which is stable under gal Q2 bar over Q2, and the quotient, which is, and then you have this kind of. You need to know, I guess, also that the determinant is the cyclotomic character. Okay, and then for L equals P, you have 2 cases. The case where P divides ABC, which for those of us who are old-fashioned enough to remember, used to be called the second case of Fermat's last theorem. Okay, so that implies that EABC has multiplicative reduction, which implies that rho ABC is ordinary, and again for that, at P, for that you again use the Tate model. Use the Tate's analytic description of the points of E over QP bar. And if P does not divide ABC, which corresponds to what used to be known as the first case of Fermat's last theorem, then EABC has good reduction. And that means that its P division points are a finite flat group scheme over ZP. And so that implies finite. Yeah. This Tate model means this description that I gave up here of the QL and ramified points of E. So in the case where L divides the conductor exactly, you have a very good control over the set of QL and ramified points because of this Tate. Yes, so it's analytically isomorphic to a quotient of this multiplicative group by a discrete subgroup generated by an element Q. So I introduced this Q in the Tate curve when I described the formal neighborhood of the modular curve. I sort of described the Tate curve over Z double bracket Q 1 over Q. And it's the same Q which is occurring here. So it's a description which is analogous to the Weierstrass description. Okay? Am I answering your question, actually? I don't know if... the curve is this one, huh? It's this curve which I wrote here. Okay? Yeah. Up to isomorphism over Q, I fixed it to be that equation. Okay? And I've normalized with these converges mod 4. The reason for doing that is so that the conductor will be a square free integer, which means that the elliptic curve is what's called semi-stable. It has multiplicative reduction at all the bad fibers. Okay, and that's what I'm using in this analysis of the behavior of the Galois representation at the bad primes, the primes dividing the discriminant. Okay. So somehow you might think that things get more complicated when you try to study the elliptic curve at the primes of bad reduction. But when you have semi-stable reduction, things almost become better because of this explicit analytic description, which is analogous to the Weierstrass theorem. Maybe I should mention this parenthetically for those who haven't seen the Tate description. So in general, when you look at an elliptic curve with the complex numbers, you can identify it with C modulo a lattice, and you can always scale that lattice so that it's generated by 1 in tau. Okay? But now, if you apply the exponential exp of 2 pi I dash to this description, you get an isomorphism of C modulo 1 tau with C star modulo Q to the Z, where Q is e to the 2 pi I tau. Okay? So this is an alternate form of the description, the explicit analytic description of elliptic curves given by Weierstrass theory. So you can either think of your elliptic curve as C modulo a lattice, which is this way of looking at a torus, or you can think of it as C star modulo, so this is the punctured plane modulo parameter Q. So it looks like an annulus like that, where you've identified these two concentric circles. Okay? Those are the two ways of thinking analytically about elliptic curves over C, which are related by the exponential map. Now, when you try to describe an elliptic curve over a local field, in general, you have neither of these two analytic descriptions. But if the curve has multiplicative reduction, then this description generalizes, and that's Tate's theory. So it's exactly that. But now, because gal QP bar over QP is more rich than gal C over R somehow, you can get a lot more information somehow about the local action of the Galois group, thanks to this analytic model, which is valid over a small finite extension of QL.
I'm sorry, but in case of P divides ABC,
yes.
in QP star, P the roots of unity is ramified.
Yes. Right. So the ordinary here is still, you still have the cyclotomic character. The difference is the cyclotomic character is ramified. And I'm not claiming that the representation is unramified. I'm claiming that it's either ordinary or finite. Both cases, ordinary and finite, do have ramification. So I do have ramification at P, but I have a bit of a control on the ramification, on the kind of Galois representation that arises. That's all I'm saying in this part 3. In this part. The case finite occurs when P has good reduction. When P does not divide ABC, E has good reduction, and so therefore its modulo of P division points is a generic fiber of a finite flat group scheme over ZP. For those of you who know what that means. Okay. And that's it. That completes the proof. That's all I wanted to say about the proof. So you sort of analyze completely explicitly the Galois representation. You get this kind of very limited ramification. So now I want to state a theorem which we've somehow already seen this morning and yesterday, the Theorem of Mazur, which gives us some global information, so global properties of this representation rho ABC. And the theorem says that rho ABC is irreducible. In other words, this EABC does not have a rational subgroup of order P. Now, this is, of course, very much in the spirit of the results which we explained yesterday in the context of Mazur's theorem on modular curves. Because saying that if EABC had a rational subgroup of order P, it would give rise to a rational point on the modular curve x naught of P. Now, what I and Marussia this morning showed is not quite that, but we showed that an elliptic curve cannot have a rational point of order P for P large enough. Okay? So, but I claim that using the same ideas, you can prove this slightly stronger statement. And I give this to you as an exercise. So adapt the, well, using what we saw, I mean, in Marussia's lecture and mine yesterday, adapt the proofs of the previous lectures on Mazur, of the lectures on Mazur, to show this. And I'll give you a hint even. It's actually not hard at all. You have enough information definitely to do this. The hint is that EABC has primes of multiplicative reduction. So if you stare at the proofs that I gave you yesterday of Mazur's criterion, actually, you'll see how you can adapt it to this situation to show that EABC cannot have a rational subgroup of order P. P larger than something. Okay, I mean, yeah, P larger than whatever. Yeah, P bigger than 30. I mean, Fermat's theorem was known for P up to 100 at the time, the time of Kummer. So certainly for this game, we're allowed to assume that P is larger than I mean, all the small primes have already been taken care of. Yeah. Okay, so this is an exercise. And so, and you see that actually we're really building. So what we've done, and somehow in the strategy of Fermat, of tackling Fermat, is to transform the question about the original question, which was a question about rational points on the Fermat curve, into a question about rational points on modular curves. And modular curves are tractable thanks to these techniques that relying on the fact both that modular curves are moduli spaces, and secondly that their Jacobians are related to modular forms. So we have sort of good conceptual tools to handle those things. Okay, so to summarize where we're at this point, thanks to these two results, I've constructed a sequence of, let me maybe continue. Okay. So sort of summarizing what we've done now. So we have constructed a map from the non-trivial solutions of the equation x to the p plus y to the p equals z to the p. We've constructed a map from this to the set of all elliptic curves of some conductor, okay, of square-free conductor, semi-stable elliptic curves. This is the Frye construction, okay? And this sort of has the same flavor as the Kodaira-Parshin construction. So we're starting with rational points. So here my curve x is the Fermat curve. looking at rational points on the Fermat curve, I'm associating to each point on the curve some curve. Okay? So it has the flavor of the Galois partition construction, so I'm going to give it the same name as I did in my exposition of Falting's theorem. I'll call that R1. Okay? But there are two key differences with the strategy of Falting's. The first, in Falting's, we were mapping this to a collection of curves which had good reduction outside a finite set of primes which didn't depend on the solution. But here we saw that the conductor n is the radical of ABC, where AP plus BP equals CP is the solution. So the bad reduction set of the curve depends on the solution. So we can't hope that this collection of curves is finite. Of course it's not. Okay? If I look at all semi-stable curves. But then we made a passage which is reminiscent of the passage from isogeny classes of abelian varieties to their associated analytic representations. So I'm going to call it R4, as I did before. But now we're looking at the mod P representations. So mod P representations, rho, from the Galois group of Q to GL2 of Fp, which are satisfying a bunch of properties. The first thing is that they're irreducible. This is by the Theorem of Mazur. Irreducible mod P representations with the property that rho is unramified outside the primes 2 and P. Rho is ordinary at 2 and is ordinary or finite at the prime P, in the sense that I stated before. So we have this sequence of maps. Okay? Now, yeah. Okay. Okay. So, okay. At this stage, I want to make a few comments. So the first comment is that unlike in our proof of Falting's theorem, we are working with mod P representations, not Analytic representations. Mod B, not Analytic representations. So these are sort of a list of differences of the approach I'm describing now and the approach towards Falting's theorem. The differences with Falting's. We work with mod P non-analytic representations. In particular, we can't, we don't know that the map R4 is finite to 1. In the case of Falting's theorem, we saw that, as a consequence of the Tate conjectures, that an isogeny class of abelian varieties was completely characterized by the isomorphism class of its analytic representation. But the mod P representation is a much kind of more delicate, finer invariant. We don't know a priori that R4 is finite to 1. In fact, we're not going to prove that. Exactly, that's the point. Yeah. Yes. Right. So that's the point, right? On the other hand, we're being more ambitious. We want to show that x of q is empty, not just finite. And so what we're going to try to do, in fact, is show that this last set is empty. So it is enough to show that this last set is empty. And at this stage, we're kind of dealing with a problem of understanding a collection of Galois representations of a very prescribed ramification given in advance. And the key new ingredient in the approach, is to exploit the connection with with modular forms. So connection between Galois representations, the kind of representations that I have here, and a completely different kind of object, which seems unrelated a priori, which are modular forms. So I'm going to give you a quick overview of that, because it's really a fundamental topic in number theory, and it's what plays the essential role in the proof of FLT, this connection between modular forms and Galois representations. So, and this is something we haven't seen before, although we certainly have seen modular forms being used in connection with Diophantine problem in the lectures of Marussia and my lectures also yesterday. But this is a different connection. This is a completely different connection. So let me say some words sort of for modular forms. Two Galois representations. So I'm going to explain to you how you can construct, how you can associate to a modular form certain Galois representations having prescribed sort of specific behaviors. So let F be a modular form. I'm going to restrict my comments to forms to the space S2 of well, now, the slight novelty is that I'm going to allow myself modular forms on gamma naught of n, not necessarily gamma naught of p, which were the only ones that we worked with until now. So an S2 of n, S2 of n with, well, I don't know, C, say, be an eigenform. Be an eigenform of weight 2 on the group gamma naught of n. And I'm going to denote by Kf the same things I had yesterday. So Kf is the field of Fourier coefficients generated by the Hecke eigenvalues. And the ring O sub f is the ring generated over Z by those same Fourier coefficients. So that's an order in the field Kf. And I'm going to also give myself a prime. So let P be a prime of OF, if you want. And let me write Kf script P and OF script P for the completions of these rings and fields of generated by the Fourier coefficients at the prime P. So the basic theorem, which follows from the Eichler-Shimura construction, which I described yesterday, is that we can associate to this data, namely the modular form, together with this, together with this prime P, a Galois representation. So there exists a Galois representation, which I'll denote by rho Fp. So it maps the Galois group of Q to GL2 of KFP, GL2 of this local field. And it satisfies the following conditions. So satisfying the following properties. The first is that rho F script P is unramified outside the conductor N and the prime P. And the second is that rho Fp of the Frobenius element at a prime L. So here I have a rational prime looking at the representation of the Galois group of Q. So rho Fp of Frob L has a characteristic polynomial which is simply x squared minus AL of fx plus L, where AL of f is the L Fourier coefficient of f viewed as an element of KFP via the natural embedding. So this is the theorem, and the construction is simply is based on the Eichler-Shimura construction, right? So the proof is to use Eichler-Shimura. So Eichler-Shimura construction associates to this form F an abelian variety A sub F, which is equipped with an action of the ring OF as Q rational endomorphisms of this abelian variety A. So now if I look at the so I can look at the p-adic Tate module, VP of AF, the thing that we considered in the context of fault. This is a ZP module, but it's also a module over OF tensor ZP. So I can tensor this over the action of the Hecke ring, the Hecke algebra, T, with KFP. Okay? So I have a map from T to KFP. By looking at the associated eigenvalue, and I can tensor it by this, and then this is isomorphic. It's a two-dimensional vector space over this local field, but which is equipped with a continuous action of the Galois group of Q. So that's the two-dimensional p-adic representation associated to the modular form F. And it's a consequence of the equality of L series, which I just stated in my previous lecture, that this analytic representation has those properties. But now, you can also do a bit further. I mean, you can also associate certain two-dimensional mod P representations, and that's important for my talk. You have certain mod P representations. The reason is that the compactness, because GQ is compact, that means that this rho, so I'll call rho FP the resulting Galois representation. Rho FP is the map from GQ to GL2FP of KFP, which I get by choosing a basis for this vector space and writing down the Galois action. Okay, so the compactness of GQ means that rho FP of GQ is conjugate. The image of this representation is conjugate to GL2 of OFP. I mean, yeah. I should take integral closure, really. So it's conjugate to the GL2 of the ring of integers of OF at P. I mean, the ring of integers of KFP, in other words. And now I can just reduce modulo P. So I can now apply a conjugation so that my representation lands in here, and then reduce modulo P, so I get GL2 of OFP modulo P, which is a finite field. Okay? And I'm going to call the reduced representation, I'm going to call it rho FP bar from GQ to this. So in other words, what I'm seeing here is that to every modular form, together with a prime ideal in the ring of Fourier coefficients, I can associate also mod P representations of the Galois group into GL2 of a finite field. Okay. So, so the key conjecture is that actually we can go in the other direction. So it's also, we expect that in fact all mod P representations should be obtainable by something like this construction. Okay? So we expect, and we have a sort of a deep collection of conjectures that say that we should be able to go from Galois representations to modular forms. And I'll just state a conjecture of Serre in this direction. So conjecture of Serre. So what? E to the E. Be a Galois representation. Then there exists, well, okay, so let me just state the particular form that I'll be needing, actually. So, which is, firstly, good or ordinary in the sense that I said before at P, ordinary at L for all L dividing some fixed integer capital N, and unramified outside N, outside the set of primes dividing N. Then the conclusion is that there exists F, an eigenform in S2 of gamma naught of N, and a prime P of the ring of Fourier coefficients such that rho is equal to the mod P representation associated to F and script P. That's the conjecture. Yeah. Ah, good point. Yes. Let it be an odd. Yes. An odd Galois representation. Actually, yeah, this is important. You're right. So odd means that rho of complex conjugation should be conjugate to this matrix, which have eigenvalues 1 and minus 1. Okay? And yeah, that's a good point. Here I should also have put the adjective odd, which is... So remind me to do that when I'll bring this board down soon and we can do that. Okay, the representation that you get from elliptic curves are certainly odd. That's not hard to show. Okay, so that's the statement of Serre's conjecture. So in the context at hand, in the particular context of Fermat's last theorem, let me sort of bring this down now, I guess. So as you pointed out, we can add odd, and if you want, I can leave this to you as an exercise to see that row of complex conjugation has this property. This is a fun exercise in elliptic curves. I mean. Okay, so then what Serre's conjecture predicts is that there should be an arrow, R5, which maps to modular forms, in this case, of weight 2 on gamma naught of 2. But modular forms are very concrete objects, and we saw that the dimension of this space of modular forms, I mean, I guess I should say maybe with coefficients in Fp, okay? But we saw that the dimension of this Fp vector space of modular forms is equal to the genus of x naught of 2. But x naught of 2 has genus 0. And so that means that this is empty. So as someone said, this is empty. So Serre's conjecture implies Fermat's last theorem. Okay? But as Marussia just pointed out, actually, Serre's conjecture is now a theorem. So this is a remark. Well, Serre conjecture is almost, I'm not sure exactly the status, but it's well on its way to becoming a theorem. Thanks to work of Carré and Vinton-Berger, which is ongoing. But this is sort of 2006, so it's very recent results. And 10 years ago, when Fermat's last theorem was proved, we did not have that result. Okay? So I'm going to sort of, in the last few minutes remaining, I'm going to just give you a quick description of how this was done by Wiles. Also because I'm going to need that for next week. So So there's a reduction. There's a sort of slightly, a theorem which is very important, but is, so we have to establish this arrow R5 from Galois representations to modular forms. It's sufficient generality to know that we can make this passage. Yeah. What is it? Well, it's a theorem in many cases. For many, yeah, and certainly in enough cases to finish it, but that would be kind of an anachronistic way of telling the story, because the work of Carré builds on the ideas of Wiles and on the cases that were first established by Wiles. So Wiles did not prove Serre's conjecture, but he proved enough of it to be able to construct this arrow R5. Okay, and that's what I'm going to explain now. What is it?
We get our representation is finite order, right?
Yes. Yeah, good. I meant finite. Finite. Yes. Okay. So the first theorem that one uses, that Wiles used, is a kind of reduction, theorem of Ribet, that it is enough to show that this Galois representation rho, or rather the elliptic curve EABC, is isogynous to AF for some modular form on gamma naught of n, where n here is going to be the radical of ABC. So if we can show that this elliptic curve corresponds to a modular form in this sense, then the p-adic representation associated to E, ABC, is related to a modular form, but of this level. Well, then what Ribet shows is that the mod p reduction of this Galois representation, because it has so much less ramification, the primes that drop out of the ramification instead of the p-adic representation, when you pass with a mod p reduction, they also drop out, or they can be removed from the level of the associated modular form. So this is this is a very crucial ingredient in the proof of Fermat's last theorem, although the statement is a little bit more technical. Okay? So this was sort of the first step in the argument. So in other words, instead of relating these mod p representations to modular forms, we're now reduced to relating the elliptic curves that occurred in this first step of the argument, I mean the semi-stable elliptic curves, to modular forms. And that's exactly the theorem that Wiles proved. So theorem Wiles that for all semi-stable, so semi-stable means that the elliptic curve has square-free conductors, so that's certainly true for these elliptic curves. There exists a modular form F in S2 gamma naught of n, such that E is isogynous to the abelian variety, to the elliptic curve that you get from F by this Eichler-Shimura construction. So n, in fact, the theorem is more precise. It even says that n is the conductor of E. So that's what Wiles proved, and of course, as a result, one gets Fermat's last theorem. So I'm going to just finish my talk by mentioning the three reasons for me why Wiles' theorem is important. Okay, and then I'll stop there. So the importance of Wiles' theorem, there are at least three reasons why this result is a key one. Well, the first one, which I developed in this lecture, is that it proves FLT. Okay? It proves Fermat's last theorem. The second reason is that it shows that all elliptic curves over the rationals correspond to modular forms. And we'll be seeing next week that the modularity, so the fact that elliptic curves are associated to modular forms, of elliptic curves is key in understanding their arithmetic properties. And we already had a foreshadowing of that. I mean, well, we know from what I said yesterday in connection with Mazur's theorem, remember that these abelian varieties, A sub f, I sort of explained that we know a lot more about them than we do about the generic abelian variety. Namely, we know that the L function of the Hasse-Weil series can be related to the Hecke-L series associated to a modular form, and therefore we have analytic continuation and so on for this L series. And then the other thing is the theorem of Grossagg-Gekoli-Wagen, which gives us a criterion for the model of ego to be finite in terms of the non-vanishing of this L series. So all this machinery, which we know for quotients of J naught of n, suddenly becomes available to us for arbitrary elliptic curves by virtue of the fact that we know that these elliptic curves are connected to modular forms. So I'll explain this more next week. This is a crucial ingredient in understanding the arithmetic of elliptic curves. So it's not just interesting for what it says about these curves of higher genus, but for what it tells us about this collection of curves of genus 1. And finally, the third reason is that this approach of Wiles introduces a general method for relating Galois representations and modular forms. And this is establishing these kind of connections. And these kind of connections are expected to exist in a very large generality. And establishing these connections is one of the major ongoing projects in number theory, in arithmetic. And I'll just mention 4 results that were kind of established more or less recently as an outgrowth of these techniques that Wiles introduced roughly 10 years ago. So the first is that in many cases the Artin conjecture have been proved following on work of Buzzard and Taylor and others. Yes, as Marussia Reboledo mentioned before, Serre's conjecture has been almost completely proved using, thanks to this work of Carré and Vinton-Berger. Excuse me? So Artin conjecture on holomorphic continuation of L series associated to finite Galois representations, to Artin representations. No. I'm not talking about the function field Artin conjecture. I mean the one that says that L rho S has analytic continuation, where rho is a representation, is an Artin representation, a two-dimensional Artin representation of the Galois group of Q. So a representation with finite image. Not completely, no. So I should say in some cases. Artin conjecture in some cases. There are some technicalities still. The third result is the Fontaine-Mazur conjecture, which I won't say anything about because I'm running late, and it's a bit beyond the scope of my lecture. And the fourth is the Sato-Tate conjecture, which has been recently established, announced by Taylor and a number of other collaborators, Harris, Clausel, and Shepard-Barron. So these are 4 major results in number theory. These last 3 have basically fallen in the last 2 years as a result of these ideas. So this is sort of very much a lively, vibrant part of number theory even now. Now, of course, this third aspect of Wiles' result, of Wiles' machinery, is a little bit beyond the scope of this lecture series, which is concerned with applications to rational points and Diophantine equations. Okay? So from that point of view, these 2 justifications are more germane to the focus of my lecture series. Now, the last point I want to make before I end is that, well, you might get a feeling from the description I gave of the proof of Fermat's last theorem that there's a point where we really got lucky in the proof. Namely, at this last stage, when I showed that this map, R5, mapped to the empty set, right? So that I had no modular forms of level 2. So we had to have very restricted ramification. So in Pierre Charolois' lecture, which is going to at 5:30, we're going to see that in fact maybe this method is a lot more general than it might seem. And so Pierre Charlevoix is going to use some of these ideas to analyze the generalized equation axp plus byp equals cz to the p, where you allow yourself to introduce fixed coefficients abc into the equation. And we'll see sort of a very general result coming out of the same machinery. And I think that actually, sometimes one mentions a Frye trick when one talks about this aspect of Wiles' proof, but I think this is more than a trick. It really is a general method, and we'd like to see it applied more commonly to other Diophantine equations. So I apologize for running over time, and thank you.